Good morning or good afternoon, and welcome to today's webinar, a collaboration between Geocomp, Olson Engineering, and Michelli Infrastructure Consulting. I'm your host, Mary Beth Michelli, President and founder of Michelli Infrastructure Consulting. Before we get started, I just want to thank everyone for your patience as we sorted out some of our unprecedented technical difficulties with Zoom 2 weeks ago. We're glad everyone is back and everything seems to be working quite well today. I am so excited today to bring together two of the premier companies in the bridge testing and monitoring industry for an informative session on data-driven decisions for bridge management, cost-effective use of NDE and SHM. Today's session will last for 2 hours with the opportunity to receive 1 professional development hour for each session that you attend. Part 1 will cover non-destructive evaluation methods on bridge superstructures and bridge decks, presented by Larry Olson, President and Chief Engineer at Olson Engineering and Olson Instruments. Part 2 will be presented by Dr. Alan Marr and Dr. Ozan Selik from Geocomp, focusing on the why and how of structural health monitoring with real-world applications. Each presentation will last approximately 45 minutes with time for Q&A at the end of each presentation. Please be sure to type any questions you might have in the chat so that we can get them answered after each presentation. Following today's sessions, attendees will receive the presentations via email with a few questions to answer in order to receive their certificates for your PDHs. So without further ado, I'd like to introduce our first speaker. Larry Olson is a PE and President and Chief Engineer of Olson Engineering as well as Olson Instruments. He is internationally known for his experience and expertise in non-destructive evaluation of civil infrastructure, including dams, bridges, buildings, foundations, pavements, tunnels, etc. He has 40 years of consulting experience in structural condition assessment and monitoring, materials, pavements, geotechnical, geophysical, and vibration engineering. He holds a BS in civil and an MS in geotechnical engineering from the University of Texas at Austin, which honored him as a distinguished alumnus in 2006. Mr. Olson also founded Olson Instruments to manufacture NDE and seismic geophysical instruments in 1995 with national and international sales. And with that, Larry, take it away.
Okay. Well, thank you very much, Mary Beth, for the introduction and hosting and coordinating this. It's my pleasure to get to speak to you today on the topic of non-destructive evaluation methods for bridge superstructures and bridge decks. So a general outline of the talk is to discuss first bridge superstructure case histories on pre-stressed and post-tension girders, concrete beams and columns, and a little bit on steel girders even. And in terms of bridge decks, looking at both concrete, asphalt overlay concrete decks, and white topping on concrete decks. A good reference is a committee I happen to be on, the ACI 228.2R13 document is on non-destructive test methods for evaluation of concrete and structures. And you can see that most of the methods, in fact, virtually all of them we're speaking on today, can be looked at in Chapter 3. And there's some information also on planning and performing non-destructive testing investigations. So the applications and the methods on concrete and steel, obviously one of the oldest non-destructive methods is to visually look at a bridge. And the bridge inspections that are done either as an NBIS biennial, 2-year, or a normal bridge inspection can be used to combine with non-destructive evaluation methods to look deeper inside our bridges to see what's inside that we can't see on the surface. So in concrete, we're looking at such methods as impact echo for concrete cracking, corrosion damage, delamination damage, honeycomb, void, thickness, and voided versus grouted post-tensioning ducts. Spectral analysis surface waves, developed by my professor Kenneth Stokey at the University of Texas at Austin, Started on in the late 70s when I was in graduate school with an office mate working on the first work, looking at cracking, crack depths, void, honeycomb, and velocity and modulus correlations, as well as predicting strength if you do the destructive testing of cores or beams to correlate. Ultrasonic pulse velocity tomography is very good for finding internal flaws, such as void and honeycomb, often used for that purpose, cracking damage as well. Ground penetrating radar, steel mapping and corrosion potential, evaluations on decks, slab impulse response. We're not going to be talking about that for integrity of the concrete and approach slab void. Infrared thermography is good for solid elimination surveys, but you need sun and have to account for staining. So top steel index, galvanostatic pulse for rebar corrosion rates, resistance, and half-cell potential, also not discussing that today. And we are going to talk a little bit on ultrasonic pulse echo for section corrosion loss in steel girders, as well as anchor bolt integrity and length. So the first case history is the classic problem of a truck with a very large forklift ran into this girder going 70 miles an hour on the east side of Denver after the poor truck driver was told, don't drive under any bridge in the United States. Well, Eastern Colorado has no bridges across the Interstate 70, and the first bridge that crosses it is in the east side of Denver, and he ran into it. Fortunately, nobody hurt. And interestingly enough, it did not fail this pre-stress, precast I-beam. It caused considerable spalling damage and cracking damage and exposed it, but not rupture the pre-stress. So the Colorado DOT decided that with an engineering design of the repairs, which was done by John Lund with Martin and Martin, this ultimately was an article as referenced there in International Concrete Repair Institute's Concrete Repair Bulletin back a while, but the article is still out there. And we did the quality assurance of the repairs with non-destructive evaluation. So you can see the many, many injection ports that were installed for the epoxy injection, sealed and injected through this 6-inch thick web, as well as the mortar patching that was done. So we were primarily checking, we did some on the mortar patching as well, we were primarily checking the injection of the cracks. We did this with 3 methods. Impact echo, where you hit impact on one side and see a resonant echo, looking for open cracks that were unfilled from epoxy. Ultrasonic pulse velocity, direct testing front to back and at an angle, semi-direct testing to different points to go through those same injected cracks. And then surface waves, which has the advantage of going across a crack. You go on each side with 2 transducers and impact at one end to excite the wave energy of surface waves. And these are all methods that are in the ICRI's guide for verifying field performance of epoxy injection of concrete cracks. It's a part of their technical guideline that is referenced to do quality assurance non-destructively, as well as, of course, with coring. This is one of the instruments that we make. It's a straightforward, economic, because it goes into your Windows tablet or notebook into an audio port, and it impacts the concrete and picks up the echo with a battery-powered handheld impact echo gauge. So the basics of impact echo, it's a fairly well-known test. As you can see, a full thickness echo down and back, resonantly those sound waves reflecting back and forth, or from a void or open crack, a depth of that. So you get in a time domain signal that you can sort of see the resonant echoes in, but that's not clear. You actually process it with what's called a fast Fourier transform, the FFT. Turns out to have a resonant echo peak. And that frequency, if that was 6,000 hertz in a typical concrete of 12,000 feet per second, factored impact echo velocity for the shape, which is this beta factor is 0.96 for a slab shape or a wall. It's lower for beams and columns because they have multiple resonances. But nonetheless, the depth's equal to this shape factor times the ultrasonic or pure compressional wave velocity divided by twice the frequency. So if that's a 6,000 hertz echo, that's nominally a 1 foot thick or 12-inch echo. So higher frequencies would be at 12,000 hertz, that would be a 6-inch echo. So this shows with that gauge some raw data on the left of the signal. On the right is the going from time versus voltage to the spectral amplitude of displacement versus frequency. And the small echo peak of that thickness is there at this, where the mouse cursor is. When you filter it to get rid of the low frequency resonance of the transducer, the high pass of 3000 hertz, then you see very clearly this small peak has become enhanced, and that echo peak is nominally 7500 hertz, corresponding to 8.5 inch thick echo at this point. So that's the basics of the test. So on the bridge girder, one area of the testing on a 6-inch grid with impact echo, out of these 9 test locations, the center point, 5, had multiple echoes. That compares to the other injected points that were all over cracks of 6.3 inch, which is nominally that web wall thickness. So this was well filled and injected. This one showed still lacking injection, 1 out of 9 in that particular area. So ultrasonic pulse velocity, there's an ASTM standard for it as well, as there was for impact echo, if you noticed. But basically, you can send sound waves through with greased coupling typically, or a ultrasonic gel if you're worried about staining the concrete. And you simply need to know the distance you're traveling, and the velocity is equal to that distance divided by the travel time from the wave from a sending transducer to a receiving transducer, and you record that signal. And you can do it directly, semi-directly at an angle, or on the surface, but here you only see an inch or 2 in, and surface waves is probably better if you have limited surface wave, limited access to only one side for testing. So a general guideline has been around a long time, since 1949, by Leslie and Cheeseman, shows that faster concrete is higher quality concrete, typically between 12 to 15,000 feet per second. Above 15,000 is very high strength, very hard aggregates, very mature concrete. It does gain like strength, velocity correlates to strength, velocity to the 4th power is proportional to Young's modulus squared is proportional to concrete strength, and you can calibrate that per ACI 228.1R. And as you get poor quality materials, it will be slower. So it's an average velocity because you're sending and receiving. In this case, we found some areas that were slower, dotted, less than 10,000 feet per second in that same test area, points 1 through 9 that we looked at for impact echo. So semi-directly testing, directly testing through, and that was faster, greater than 11,000 feet per second. So spectral analysis surface waves testing involves the bar typically with 2 displacement transducers spaced a distance apart and impact the concrete. And this method depends on velocity of the Rayleigh wave being equal to frequency times wavelength. You might remember that from freshman physics, or you might not. So what do you get? It does measure the propagation speed of surface wave with depth or wavelength. It's approximately, in uniform concrete, wavelength is approximately depth. And then short wavelength sample shallow concrete, longer wavelength sample deeper. So you get a velocity profile versus depth into the concrete. You can see if it's faster or slower, about the same. And it will indicate the modulus of the concrete, the relative strength, if you haven't correlated, and the perpendicular crack depths are all provided with this test. So this is some of the equipment we make and use for it. We have a ruggedized Freedom Data PC that does a lot of different tests, modular based, big batteries, and briefcase sized. This is the SASW bar. You can see that that's a 40 centimeter length. You can add on an extension to go out from 6 centimeter spacings, as close as 6 centimeters between the 2 displacement transducers, out to as far as 80 centimeters when you add on the extension. You've got really large and really thick concrete, large spacings. You can use small accelerometers that are attached magnetically to grease-mounted flat washers on the concrete, and you can spread it out much further and see it even deeper. You can see approximately twice as deep as your bar spacing. The NDE 360 is a smaller, handheld, portable platform that does many of the same tests as the Freedom Data PC, and it's more field portable. So it can also do surface waves, pulse velocity, impact echo, a whole range of tests as well. So what do you get? In the time domain, which is time versus voltage, you get literally the big spike is the 67% of the energy that goes into a surface wave when you impact the surface. About 26% is shear waves, and the compressional wave that we use in impact echo testing is only 7%. So it's a high energy peak, and it's the slowest wave of the 3 wave types. It's about 56% the speed of a compressional wave and 10% slower than a shear wave. So that just shows the spacing. From this information, though, you calculate the phase. And that shows, in a simple sense, you're looking at coherence in the top. So from 0 to 12,500 hertz, pretty good coherence. Above 0.9 is very good. And sometimes gets decent phase even when the coherence starts to drop, as you can see on the right at high frequencies, 13,000 hertz. But this basically means that wrap phase, you could unwrap it and be one long phase plot. This is very uniform concrete, fairly thick. It's right here at the zero crossing. It's minus 360 degrees out of phase. What does that mean? That means that the response of the far receiver, the wave gets to the closest receiver first, then it travels on to the far receiver, and if you're going between the two, it tells you how much the response of the far receiver lags the response of the close receiver. So you say velocity equals frequency times wavelength. Well, minus 360 degrees out of phase is one wavelength. Minus 720 degrees out of phase, right here, is two wavelengths between those receivers. So that would be 1.31 feet. This is 2.62 feet. That was the 80 centimeter spacing. Multiply that by the 2628 hertz crossing frequency, and you get 6,900 feet per second. That is the surface wave velocity at that wavelength. So you plot what's called a dispersion curve of velocity versus wavelength. And this shows nominally, here's the scales of 0 to 8,000 feet per second. It's nominally 6,900 feet per second, very uniform, from wavelengths of 0.8 feet to 5 feet, which is the thickness of this thick piece of concrete. So that's telling us that's sound concrete. So what do we get on the epoxy testing? Much closer spacing. We're only a half foot apart on the surface wave bar. But basically, we showed, in this case, an epoxy-filled crack had a good velocity, 7,000, 8,000 feet per second, from wavelengths of 0.18 feet to a half foot, the thickness of the web. By comparison, another test in that same area that showed some lack of filling showed velocity was slow at near the surface at 1/10 of a foot. It rose from 2,500 to ultimately 5,000 feet per second, meaning it was somewhat better filled with depth, but still not nearly as close, showing really unfilled conditions versus the sound filled crack. So we used all this together to map out and check the quality assurance repairs. They did an excellent job. There's only about 3% of the locations that they had to go back and re-inject. So a very successful repair of that bridge girder. Okay, shifting gears slightly, one of the common problems in post-tension ducts in bridges and buildings is poor grouting. This came to the attention of the country because of problems on the Sunshine Skyway Bridge, not in the girders, but these large piers that were designed for ship impact, and you can see they're protected. They had a U-shaped post-tensioning going down and back up in the duct, and they had difficulty grouting it. This is a bit older bridge in the Tampa area, but nonetheless, they found a lot of corrosion. This raised concerns which the industry, the American Segmental Bridge Institute, among others, has been working hard to get better quality assurance, better grouting procedures, better grouting materials. So it's greatly improved since the early days, but nonetheless, it's still a concern. So I had an idea sitting on an airplane after endless point-by-point testing one day that became a US patent back in the 90s of rolling and impacting the concrete instead of just point-by-point impact echo testing. So just as in the handheld device, you have a displacement transducer and impactors. This is a solenoid impactor, small one for higher frequencies, a heavier one for a little lower frequencies to see a bit deeper. You can pick either one. Every 1 inch as this spring-loaded wheel rolls along a smooth concrete surface, needs to be structural quality, fairly smooth concrete. This is not designed for rough bridge decks. We'll talk about scanning those in a bit with different designs. But nonetheless, this produces a result every 1 inch, and you get a lot more data, a lot of data quickly. So you can scan, handheld. So we were fortunate to get a grant from the National Cooperative Highway Research Program on their IDEA program. And we were also fortunate to be donated a girder by a local manufacturer, because unfortunately, the ducts ended up incorrectly draped. So they couldn't use the girder on a project. We used 20 feet of it and grouted in defects. These are nominally 4-inch ducts, and the wall thickness is 10 inches. So this just shows creating voids. So we created voids in the research project. We had a local contractor grout the voids in place, and after 3 days simulating like a new bridge condition, the grout is not that hard. we decided to test it for quality assurance of the grouting. So basically, you see a fully grouted duct here that predicts 11.17 inches because the grout is softer and not as hard as and strong as it's going to be with more curing. But still, that's a sound thickness echo of a well-grouted duct. By comparison, an empty duct where the styrofoam void filled it completely came up with 13.65 inches, almost 14 inches. That frequency peak shifted downward. So there was a 22% apparent increase in the thickness of the echo due to void. So why does it do that? It's less stiff. You can think of it as, because there's a hole in it, it's going to resonate at a lower frequency. And so that resonant frequency echo is associated with being an empty duct. So we plotted it all up on a color scale going from, as you can see, the nominal 10 inches that it is. Here's the concrete above and below the 4 ducts. This is the very top duct and the constructed defects that were in there. And you can see that we show in the color scale the effect of those defects getting thicker and thicker. It's interesting at the end where we had to have grout relief that we ended up with void conditions at the end of this where the grout was free to come out. So this is taking the same data with a skewed 3D view, and you can see it popping up from 9 to 14 inches. The top duct, the next one, and the bottom duct, which was supposed to be well grouted, and largely was, for comparison's sake, at one side of this wall. So from this, we've gone on to test a number of bridges, over a dozen bridges in the United States, to check old and new bridges for grouted versus ungrouted conditions in post-tensioning. This bridge is close to our office in Wheat Ridge, Colorado, the west side of Denver. And this shows they first had us test an ungrouted girder in the precast yard, similar to our research, except it was totally ungrouted. So we found the 4 ducts were together. They produced 10-inch echoes versus the solid wall. It was nominally a 7.5-inch wall, had 7.5 to jumping up a little bit to 8-inch echoes, but basically 7.5-inch thick echoes. That shows a result with the time domain signal and the spectral peak predicting 10 inches right here. So we proved we could find it. We took enough data that we could actually, normally we would use radar to locate ducts in walls, ground penetrating radars I'll talk about, but we had enough data taking it every 3 feet along the length of this that we could plot up where the ducts were based on our impact echo scanning. They were all avoided because it's ungrouted. It's not been taken to the field and put in place and tensioned and grouted. So then we went to the field to test the actual bridge where they had some concerns about the grouting of ducts. So we chose to test from the outside. On larger bridges, we've tested from the inside. It just depends on access. And pushing an early version of the scanner up the wall. So we did that nominally every 3, 5, or 10 feet on most projects, depending on, if you find a problem, you can close your spacing between your vertical scan lines. You can make that tighter. So the sound wall again showed 7.5 inches, but it jumped up in one location showing 1 duct at a 10-inch echo. So we knew this was voided. And they confirmed that by drilling in a borescope to look inside, which is normally done, and then you do your grouting repairs. So that worked out well. This showed another result that we found some debonded ducts because it was a curved girder like the one I showed earlier. That actually resulted in tension at the backside and a crack forming that predicted a 5 to 6 inch crack echo. And that was due to the curved girder pre-stressing of the post-tensioning. There's still a thickness echo here, but we're also seeing this crack echo. So 2 echoes in this case, 2 resonant echoes. So we participated. The NCHRP program had a grant, 1428, for inspection guidelines for bridge post-tensioning and stay cable systems using non-destructive evaluation methods to the Texas A&M University Transportation Institute, done by Dr. Stefan Hurlebau. This is their large test girder that they constructed with initial blind. Nobody knew where the defects were, and they invited various groups to test for these purposes. Here you see us scanning on the outside with the scanning unit up close there. More importantly, we scanned the inside, plus we looked at the external tendons. So here's an example scan from the inside done up the wall, and you can see the 300 millimeter web thickness here. There was a grouted duct here, it shifted it some, but the ungrouted duct shifted it to a much greater, where this is 0 to 750 millimeters in thickness, nominally 30 inches. So that is a scan result of the time domain, and there's that echo peak corresponding to this grouted duct result. So we plotted that all up on a color scale again, where it is nominally 300 millimeters thick, and in the wall here, not as thick as that other area. But basically, you can see where it got much thicker. And we're showing potential voiding versus better grouting as it moves into the blues. When you look at the inside of this large girder, you see the cables, the external tendons. And we tested those as well. We adapted the scanner with extra wheels to match the curvature of the 4.5-inch outside diameter external tendon duct. And so where people have been doing acoustic sounding with hammers and listening for a hollow sound, much like you do on a deck, listening for that within 3 inches or less delamination echo, that hollow sounding, shallow delamination that you hear in chain dragging and hammer sounding. We're doing that similarly, but recording the resonant response to identify areas of void. So it's testing every inch as that's rolled along. Here's one scan line over a distance of about 4.5 feet. The high, and this actually, we looked in the time domain. The best signature we got in the clearest, because it's not a pure resonant echo, is we saw a lot of energy in time versus voltage, and that's what's plotted here is the energy of that signal. This was an area of void. Another area of void down here from 0 to 1 foot, and better grouted conditions in between. So this worked out to be very accurate at identifying it. So over a dozen bridges have been tested. Good agreement in general between the post-tensioning ducts was confirmed, where we predict the defect with impact echo scanning with a borescope. Voids have been filled with air and water. We did grouting repairs. We've tested bridges with 1 or 2 rows of post-tensioning ducts. And fully grouted plastic ducts can be detected and verified as being grouted, even if the ducts are partially debonded. If it's totally debonded, it's a problem for a plastic or metal dip. They were grouted. We've sold a number of our systems for this to China because they have used so many post-tension bridges in all their construction. So we've got a fairly good sized number of units that are being used in China for quality assurance. The TTI research showed the impact echo results were fair to good for grout void detection in internal ducts. They were excellent with a 90% accuracy for finding grout void in the external post-tension ducts, which is a simpler thing to test. So they're just a question to think about as you take the exam later is shown is how is the presence of void in a post-tension duct indicated by the impact echo scanner results. So shifting gears to ultrasonic pulse velocity testing of a structural column, 5 foot by 5 foot by 33 foot tall column that actually supported and does a digital sign out over an interstate in Colorado. And so they noticed that there was some mortar placed on their column and they cut into it and chipped at it and found out there was significant honeycomb and void. And unfortunately, the contractor's employee was leaving the company and not happy and didn't bother to consolidate the concrete. So left a going away present, unfortunately, very unethical, of course. But they wanted to check it now. The Colorado DOT wanted to see by testing it with ultrasound how much void and honeycomb was there. Could they repair this column or not? So we did a 1 foot test grid, north to south and east to west with these ultrasonic transducers that you saw earlier and grease coupling, like lithium grease, so it's not two staining of the concrete. So this shows good signal. Time 0, you hear the pulse, it goes click. You excite the sending source transducer and the receiving transducer, 50 kilohertz natural frequency, receives it and responds strongly and shows at 372 millionths of a second. That corresponds to a pulse velocity of 13,500 feet per second. So this was a sound result. By comparison, an area right next to visible honeycomb void, you can't test on the void, showed a much weaker signal, slow a time of 552 microseconds, a very slow velocity of 9,100 feet per second, and no real amplitude, where before it was over 10 volts plus or minus. Now it's only a few tenths of a volt. So we could have given them a table of 330 values of the speed of sound through ultrasound through their concrete, but we decided to do tomographic analyses. And velocity tomography is you can do straight ray analyses depending on your access to a column cross section. You could have transducers at different locations all the way around it for really detailed testing. And you can analyze that data with straight rays or letting the data bend the way it bend to find the fastest path. So we usually run a few analyses of this and then finish with some bending or curved ray analyses to get the best image or picture of internal concrete conditions. So we had tested north to south and east to west. You have to have crossing ray paths or crossing test paths. So these crossing test ray paths going on a 1 foot grid, a simple grid, and vertically 1 foot as well, is what we did for the testing. So the computer algorithms take this data and adjust the velocities of the pixels and until the data matches. So what that means is the good was above 12,000 feet per second, this green area. Down in the lower right, the north side is where you saw that honeycomb void earlier. And then it turns into the reds and oranges and yellows, which are much slower for much of the column. Unfortunately, the column had to be torn out because while 16 of the 32 tomograms, these horizontal cross sections of the column from testing, were all green. 16 of them had a lot of red, orange, and yellow, much slower velocities. So they decided they could not repair it. And just by sheer dropping the concrete up to 33 feet, they got some consolidation. So this is another project where nothing was done wrong. There was just an enormous amount of steel in these piers of this bridge. And so it was difficult to always get good concrete consolidation. One area was of concern. So we ended up doing semi-direct testing on a 6-inch grid at several locations on the one pier with this surface visible honeycomb, minor voids, and testing around this site with another grid matching it. So by doing that, we could slice the data in a sense and look at where, in this case, down into the blues and slower, are the slow velocity materials versus the green being 12,000 and higher. You can see at different elevations where the void and honeycomb is, and it's honeycomb in this case, that they could then drill into epoxy inject and repair it. The problem with void and honeycomb is that if you lose just 5% of your normal density from normal consolidations that you drop from 150 pounds per cubic foot to 142.5. Research by the CTL, the Portland Cement Association, has shown that that corresponds to a 25 to 30% drop in strength. So every 5% loss of consolidation from normal is a tremendous penalty in terms of strength. So they use this to guide their epoxy injection to fill these small honeycomb and void areas. So tomography takes training experience for analysis, but the field data is straightforward, but you have to be careful about it, and it takes a while to do it because it's many more tests. You can do it with angled and direct tests. You have to have crossing ray paths, crossing test paths to image the concrete. Otherwise, it's just an average velocity. If you're just going straight through, it's just an average. So a picture is worth 1,000 words. It gives you a much better image of your void and honeycomb. So how is the presence of more severe cracking in honeycomb void indicated in the signal, in the ultrasonic pulse velocity signal? Is the question here. A little bit on ultrasonic thickness testing and flaw detection for corrosion and flaws in steel. This just shows a 5 megahertz probe testing this to check for internal corrosion. If it's not visible on the outside, assuming, it'll be a thinner echo. So you would see a thinner echo than your normal thickness echo in the ultrasound, but it's much higher frequency. These frequencies are so high, they just scatter in concrete. You can't use a metals ultrasonic transducer on concrete. So this just shows up in the upper Midwest on an interstate system, steel girders, where it was built in the 50s, and they had the classic problem of the drainage went towards the joints and down onto the bridge piers, the abutments, and of course, any beams that are below those joints. So these cross beams. Then it ran down the girders themselves until even at midspan, it was ponding and there was corrosion and loss of section, up to 60% loss of section. This shows doing that type of ultrasonic testing with a flaw detector. It's not just a thickness tester, which only shows you the number. This shows you the signals. So here's an example of bolt testing. Bolts are often of concern in terms of potentially broken and cracked, depending on the loading. We found cracked short bolts that were broken. This shows an echo of 6 inches. This bolt was supposed to be a 24-inch long bolt. So this echo is showing 6 inches. So it's important to check your anchor bolts in most projects to make sure they are in good shape. So now we're going to shift to bridge deck condition assessment methods. We mentioned the visual. We're going to talk about impact echo scanning and surface wave scanning for asphalt overlay decks, impact echo for concrete decks. Ground penetrating radar is not as good at mapping out the damage, but the potential for damage it's good at, and it's excellent at mapping the depth of the steel for cover and service life evaluation. We won't talk about infrared or galvanic pulse. We will talk a bit about supporting destructive coring and laboratory tests for checking the NDE results and service life estimation. So this shows a deck scanner that we've developed. It's our sonic surface scanner. It can also be used on asphalt pavements for debonding of asphalt lifts and slabs. So you push it along and you're impacting in these 2 rolling wheels as you push it every 6 inches. So look at the concrete quality, find top and bottom delaminations. If the top one is not present, you can check for a bottom delamination with the impact echo test. So here's a close-up of the unit. You can see the solenoid impactors, and these are the brass displacement transducers that pick it up. We have just recently added GPS, kind of a prototype. We think we can shorten it by 1 pole section now. We don't have to be quite that tall unless we've got some interference. But this will now map it to, with a base station and a good quality GPS, less than 10 centimeter accuracy of the test points. So as we roll along, we are now slow walking it just a mile or 2 an hour, and we're rolling along on the decks. Now it's designed with these displacement transducers, push out, contact the rougher concrete of a deck, and you hit it sharply with a solenoid impact. So as this rolls every 6 inches and touches the deck, we are getting a test result. This one was a brand new bridge, and the concern was actually that the concrete set up too fast in the Southwest US, a couple hours out of Las Vegas, and they had a bunch of drying plastic shrinkage cracks, but they were worried there might be a consolidation problem because it was relatively hot and it set a little too fast before they could get it perfectly placed. So we did, in 1 day, 42,000 impact echo tests for every half square foot deck coverage. The wheels were spaced 1 foot apart, testing every 6 inches. So we're testing very fast, about 10,000 square foot an hour. So this shows the underside of the deck. You can see the girders, the cross beams and diaphragms. And it was tight enough against the deck concrete that we could see the effect of those thicker elements. This shows before we had a cart, just pulling in on a simple wagon on the deck. And you can see that it's fairly rough, but the wheels are heavy. We got good quality data, even through this rough deck. This shows a 100-foot scan line, that's 200 tests, about 12-inch thick here. This is 0 to 30 inches, 0 to 100 feet. And then you come off the approach slab onto the actual deck, and it's nominally the 8-inch thickness that was expected. Had there been void and honeycomb, we would have seen a lot thicker than that. And there's an example of the signal quality from this point, showing a nice strong time domain signal and the resonant echo at 10,000 hertz, which corresponds to 8.05 inches. So we took all this data, plotted it up on a color scale again, and you can see where there are those girders, the diaphragms, the thicker sections, but we didn't find a lot of excessively, well, really any to speak of, excessively thick concrete that would have indicated void and honeycomb, because it shifts it just like the impact echo scanning on a voided duct shifts it when it's voided. So this was a project that we worked on, again, as a volunteer participant in the research. Rutgers University had a SHARP 2 grant for the R06A for research on non-destructive testing of concrete bridge decks. So this is until March of 2019, I was in our Metro Washington, D.C. office in Virginia and used to drive over this deck regularly. But this old deck over I-66 was a good study deck in Haymarket, Virginia on US Highway 15. So basically, they studied this area greatly. It had a bunch of corrosion. When they removed and replaced this bridge, the section ended up at Turner Fairbanks, FHWA, their laboratory in Langley, Virginia, or McLean to be precise. But in any case, this area was the study area. So what you get in impact echo is hopefully a sound thickness echo, which is this peak. If there's a tight crack, you can see an echo from the depth of the crack, which is the higher frequency, and still a thickness echo that might be shifted a little bit, where there's still enough contact. If you have a deeper delamination, you would see an echo peak that corresponds to a greater depth to that delamination if your bar is deeper, like top versus bottom steel. And a top delamination makes, which is the hollow drummy sound we all hear when we use a chain drag or sounding with a hammer, that's a flexural resonance. That loose piece of concrete within 3 inches or less shows up as a flexural resonance in the impact echo test as well. And that hollow drummy sound is the flexural resonance. So what do we get? This shows a simple color scale where red is severe delamination and yellow is incipient of the top steel. And that Rutgers University had done the sounding study, the chain dragging, and see very good agreement between the chain drag and the impact echo. There's more detail in the impact echo scanning because you've taken the human ear out of it. But nonetheless, they are similar, except for over here, as I'll comment on further in a minute. So this shows, though, with impact echo, you can also find where there's not a top delamination, you can see bottom delaminations. And this is the light blue color. This is bottom steel. So there's some corrosion at the bottom. And we quantified it areas with probable top delamination, about 14% in red, incipient, top delamination, 13% in yellow, and probable bottom delaminations of 5.7% in light blue. And sound concrete was 67%. So this deck is definitely was a candidate for repair, and it was later replaced. They should have said replaced. It was not going to be repaired. VDOT tries to get their decks well maintained. When it gets this bad, they're going to replace them. So we also did ground penetrating radar and used in this case a IDS unit. It's a 2 gigahertz bipolar antenna. And that means it has front and back and left and right antennas. You can get images for 3D imaging if you do it closely spaced with one direction scanning. So this just shows how you can get images of rebar on a grid and the idea of front and back antennas and left and right antennas being done simultaneously. So it's a bipolar or full polar scan. So what do we get? Well, this is an example of just showing the difference between the front to back, which is the VV, and side to side, HH. You can see the rebar, depth of cover to the tops of rebar, and that it's closely spaced. But you didn't see these deeper features well at all. This is actually post-tensioning at a larger diameter than the rebar, and you can see that in the other direction scanning. So it's a good way to locate post-tensioning behind rebar with dual antenna. And that's what that's pointing out. So comparing everything from the sonic surface scanner with impact echo to the ground penetrating radar, which was calibrated based on the impact echo results, because you have to decide a threshold of attenuation in radar and correcting for depth of cover in the bars, and chain dragging. So they were very similar, the scans, more precision again in the impact echo than in the radar or the chain dragging. One interesting result where they cord things to check them is in the upper right, you can see the 3.5-inch core result, the impact echo predicted delamination. They did not hear it in the sounding. It was too deep. They did hear, and impact echo likewise predicted delamination here at this location of core 5. So generally you can't hear much deeper than 3 inches in our opinion. This just shows follow-on work we did with the cart and using our big PC before we used a smaller Dell ruggedized notebook with an excellent screen and sunlight on it. But here we are at the National Center for Asphalt Technology, scanning for debonded asphalt pavements, so-called delamination of hot mix asphaltic concrete. They had built a test section, initial blind testing again, and we learned from that we could, using surface waves, do a good job of discriminating debonding of the asphalt lifts, which can happen on projects in the real world from dust storms, other things that lack of bonding of the tack coat to the next lift. So this shows you ultimately line up the receivers when you're doing surface waves, and we typically space them 6 inches apart. So we hit on the left, we get one test between them. So what we found on their study, and we became a selected vendor to go on to the second phase and develop technology further, was nominally 5,000 to 5,500 feet per second was a bonded asphalt. No debonding of the lifts. On the other hand, when they put in a delamination from thin paper, they also used dust to simulate delaminations at 2 inches and 5 inches. This was at 5-inch deep thin paper debonding simulated delamination, and it dropped in velocity from 5,300 feet per second at nominally a wavelength of 0.43 feet or 5 inches, and it was 4,300 feet per second. Drops in velocity because there's a lack of contact. It's lost the bond. It's not as stiff. So that slows down the surface wave energy, and we see that. So basically, that gave the best results of predicting asphalt pavement delaminations. And we saw the slower velocity drop at the depth of the delamination. This led us to try out a demonstration study internally for the Colorado DOT to see if we could still do some work on asphalt overlaid concrete decks, which are more difficult to test. You can't really do impact echo or sounding well through asphalt. It's normally too soft and may not be bonded. It'll sound hollow. Infrared thermography is hard to get the heat source to go down and be more sensitive in the first 2 or 3 inches. Impact echo scanning, asphalt often absorbs the energy unless it's colder, concrete-like, but it still can be debonded. And radar is complicated by de-icing salts and moisture. That was hard to find thin delaminations. Also, it did not work well for that on the asphalt debonding, unless they had put water into the interface, and then they could see it because of the change in dielectric content. So surface waves did detect the delaminations of the asphalt pavement lifts. So we extended it to the asphalt decks. This shows the 2 sensors lined up. We got an impact echo result on the left and surface waves between them spaced 6 inches apart. So we did this scanning on 2 decks that were going to be repaired by the state of Colorado. This is what we found. This was bonded asphalt and sound concrete. 2 signals, big spike of surface waves. Here's the phase plots. That was a smooth, nominally 5,300 feet per second result. No debonding, no delaminations. This showed a result with asphalt debonding. This delay in phase corresponds to this drop in velocity from 5,500 to 4,500 feet per second at 3.5 inches deep, or wavelength of 3.5 inches. This showed bonded asphalt, that was okay, but there was a top steel delamination. This delay in phase here corresponds to this drop in velocity from 5,800 to about 4,800 feet per second at a wavelength or depth of 5.1 inches. That's deeper than the asphalt, that's the top steel. So this was indicating a delamination due to corrosion of the top steel. This result, which had both at higher frequencies, asphalt debonding at 3.2 inches, a drop in velocity, and then this drop in velocity occurred at the bottom steel at 7.4 inches deep. So we predicted and gave them Colorado DOT a report prior to learning what they found. So this is our plot from 50 to 70 feet, 48 feet in. They came in and scraped off the asphalt and then used hydrodemolition to clean up the concrete. And that's going to remove the loose delaminated concrete that's already spalled and cracked due to corrosion, expansion of the rebar. So you can see that where we're predicting this shape of defect here, it's outlined and agreed very well. That's 60 feet and 70 feet to the photograph. And then as up here in this area is an area of delamination as well that we also detected. So on this basis, we've gone on to test 30 other decks for Colorado DOT where they have asphalt overlays. Maybe it's about 20 decks thinking about it. But nonetheless, we've been able to check this with good accuracy. In many cases, they were able to save doing anything because they now knew it was still sound concrete underneath the asphalt. Other cases, they had to repair. Final case history on deck scanning for detection debonding is a white topping overlay of a concrete deck in Texas. They were worried about debonding, pushing the cart along on a 1-foot grid doing impact echo. And we mapped out areas of partial debonding in this color, sound concrete debonding condition in this color, as well as shallow laminations with a low frequency response. So it's useful for finding out debonded versus bonded white topping. So I think the summary, I've pretty much already given this. GPR is not sensitive to bottom delaminations. It's better at mapping damage potential and certainly going vehicle speed. It will go vehicle speeds, not the more precise impact echo scanning on a project level survey. Surface waves is good for mapping out delaminations of asphalt overlay decks and pavement lift debonding. And impact echo scanning found the white top deck. Your last question would be, which NDE method for the sonic surface scanner can detect concrete deck delaminations below an asphalt overlay or debonding delamination of asphalt pavement lifts? Very quickly closing it out, we've got cores and typical laboratory tests are done. We do a lot of detailed deck studies and recommend repairs. The chloride tests are done typically from core samples, assess the susceptibility to corrosion, and estimate the remaining surface life as the concrete acidity increases due to chloride penetration. Phenolphthalein tests, we normally do these on the cores right away in the field, clean them up, photograph them with a tape measure. That's to get the depth of carbonation from carbon dioxide coming in, which can also lead to long-term corrosion of reinforced concrete. Again, estimating the remaining surface life, again, it makes the concrete more acidic and lead to breaking down the passive protection layer around the steel from the concrete and corrosion. We also do compressor strength, unit weights, ultrasonic pulse velocities where we want to correlate to strength. We do petrography if it is concerned for long-term performance of the concrete. Look at the degree of hydration, air void spacing and size, alkali aggregate and alkali silica reaction problems, fire damage, water cement ratio, et cetera. And certainly we're working with laboratories. We do our own chlorides testing generally in phenolphthalein, but we're working with laboratories to do these other tests. So this just shows taking cores in the field. You can do pulse velocity testing, as I mentioned earlier. Velocity to the fourth power is proportional strength, but you have to correlate with the core. You're going to use it to predict strength. There's procedures in the ACI document 228. This shows taking some samples out for rapid chloride testing in the laboratory. These chloride concentrations are above the 0.33% typical threshold that could lead to corrosion if your steel was at this depth. So that's a typical threshold by weight of concrete. So this shows some common thresholds from Sharp research. 0.03% by weight of concrete or 0.2% by weight of cement can lead to rusting as the chloride levels reach that at the depth of your steel. That's where the radar comes into it. You get depth of cover from radar. Different concrete conditions have different thresholds. It'll vary. It's not an absolute thing. There's references in the literature. We apply fixed second law of diffusion, as do others, for remaining surface life estimation. So by doing this, knowing the age of the bridge, the chloride diffusion, the chloride concentration levels with depth, we like to test at least every ½ inch to do that. This is very detailed testing, but the idea here is surface chloride content. You usually have to interpolate that because it gets washed out in rain in the summer. But you have a best fit line for your curve. From that, you get the diffusion coefficient. You go into Fisk's second law, and this just shows there's a threshold of 0.03% was applied by weight of concrete, and you can see the different curves for 200 years remaining at that if your steel was at a cover depth of 68 millimeters for this particular site. And 50 years remaining is showing, okay, if your steel hits this depth, this is depth of steel on the bottom. So you can evaluate your risk and how much corrosion is projected to occur in the future before you have to do maintenance or replace the deck. Carbonation, penetration depths are done with phenolphthalein testing, spraying it in the field on a washed off core with a tape measure. Basically, it's the clear area. In this case, it penetrated about 7/8 of an inch, shows the depth of carbonation. So again, there's an equation you apply for that. Based on the age of the bridge, you can predict the time to corrosion initiation for the depth of steel. So I want to thank you very much for your time and attention today. Very happy to answer any questions afterwards. My email was given at the start. And I will turn this now back over to Mary Beth in case there are any questions. And thank you very much for attending our webinar.
Thank you so much, Larry. That was super informative. And I think probably a lot of people who are here today probably have had these tests done before in some way or another, especially the cores. but didn't really understand how the remaining service life is calculated. So I think that was really important for people to get an idea of where these numbers come from, where these reports come from. So we have a couple questions here. The first one is, are impulse echo scan results user dependent? Does the test produce consistent, repeatable results regardless of the user?
The impact echo test does produce repeatable results regardless of the user. You have to be, of course, you still have to know how to do the test properly and recognize that you've gotten a good impact and a good response. But in the impact echo scanner in particular, and even in the point-by-point testing, the software is advanced to where you can tell that fairly readily. It was shown to be ultimately, and Glenn Washer, formerly at the FHWA, but now a long time at the University of Missouri at Rolla, looked at all this SHARP2 research, and it was the most accurate method for finding delaminations in that study. It's really a very good project level test as opposed to a network level high speed scanning test with, say, ground penetrating radar on a vehicle or infrared thermography on a vehicle.
For sure. We have one more question that says, what is the ballpark cost for the different type of tests? Maybe base it on a square area, and maybe just sort of talk about a couple of tests.
A lot of what I showed you today is very much a forensic investigation, meaning you're trying to find some damage and other problems. So a nominal cost for us is, like, not counting mobilization or travel, is typically it'll end up running like equipment analysis and report, all the charges except mobilization travel, nominally $6,000 per field day. And you get a lot of tests for that. It depends on what you're doing. Even point by point, you can get 400 to 500 impact echo tests in a day. And surface waves is a little bit slower, but you still get a lot of results for that charge.
Okay, well, we have a few more that just came in. So let me, we'll go with this one. How widely accepted and implemented are these technologies? Do you find chain drag and hammer sounding still widely used?
Well, of course, chain drag and hammer sounding are still widely used because your normal, and I happen to be, as an engineer, I became an NBIS certified bridge inspector because of our work, and we will do that, not as our mainline work, but we do it in support of our clients' projects to give it an NBIS rating. So technicians can be readily trained to do that. You just don't want somebody who has a hearing problem, obviously. I would say it's getting to be more and more widely used. The specialized technology, the sonic surface scanner, we've only sold to a couple of DOTs, the Iowa DOT, and in particular Indiana DOT now has a couple of units, and they are using it for their detailed project level surveys of all their bridge decks. So it's being accepted more and more by the DOTs, and certainly FHWA, they have a non-destructive evaluation center that's headed by Dr. Hoda Azari at Turner Fairbanks, and you can go to their website as well and see a lot of this technology. So the answer to his question is, the bridge industry is very much moving this direction, and they've been seeing these technologies. The technologies are getting better, and we do a wide range of things, including even network level surveys, but you get more detail from a project level survey.
So I think we have time for one more question, and I see that there's quite a few more. So what we'll do is, if we have time at the end of Dr. Selleck's presentation, we'll answer a few more then. If not, we'll get all of your questions answered in an email out to the attendees today. Okay. So the last question is, what is the recommended NDT to be used to evaluate the condition of a bridge concrete deck, which is covered with waterproof membrane and asphalt?
Okay. Yeah, presumably the waterproof membrane, of course, is between the asphalt and the underlying deck. We would recommend, if it's tight enough, and depending on the membrane, still do the surface wave scanning to go across that. Recognizing, though, that we'd have to be sure for that particular membrane that it wasn't too thick and soft, that it would prevent seeing deeper. The membrane is also going to be a problem for radar in terms of dielectric constant. It's going to be an insulating membrane. So that would be the case. We've done decks like that successfully, but like I say, if it gets too rubbery and too soft and too thick, it's going to be problematic. We could certainly scan from the underneath side. and rig up something special. And there have been studies that show infrared. Now, granted, most decks have problems on the top side unless you're close to the ocean, when sea salts will affect it top and bottom, more so. But as you saw even from the Virginia deck, that is not close to the ocean. That is very much just, you get some corrosion at the bottom, being real capricious, as Mary Beth well knows.
Great. Well, thank you so much, Larry. We really appreciate your presentation today. And I think we can switch over to the Geocomp presentation. Maybe Larry has to stop sharing. So in that case, though, I will hand it over to Dr. Alan Marr, who will introduce Dr. Selick and talk a little bit about their presentation today.
Thank you, Mary Beth. Can you hear me?
Yes.
Good. I always like to check the fundamental part of Zoom these days, right? Yeah. Thanks, everyone. Just for your interest, we have 222 folks listening in on this, and it's been pretty steady all through Larry's great presentation. We appreciate you joining us on this, and hope you find this a valuable use of your time. Ozan Selick is a PhD from the University of Central Florida. He's been with us a number of years. He's been our lead on the large new Tappan Zee Bridge project across the Hudson River, also known as the Mario Cuomo Bridge, which is one of the more recent high deployments, executions of structural health monitoring in the United States. And he's going to talk about that a bit, along with many other things. Ozan's strong interest and capabilities, having been trained as a structural engineer, are in structural health monitoring, lifetime assessment of bridge components, and in computer vision as a means of assessing surface features on transportation assets. So Ozan, we look forward to your presentation. Thank you.
Thank you so much, Alan. Everybody can hear my screen. Can see my screen, I'm sorry. Hello, everyone. Thank you for your time today, and thanks, Larry, for the great presentation. Hopefully, our presentation is going to complement what we started and then wrap it up in terms of how we can successfully investigate the health of our structures and then move forward by doing successful remedial actions. So here I'm going to try to talk about structural health monitoring. So we are going to talk about what is structural monitoring, why we need structural health monitoring, and how it can be implemented, successfully implemented on various projects.
Excuse me, Ozan, but I'm having a little trouble hearing you, so maybe adjust your microphone or something. I'm a little hard of hearing too, but maybe others.
How about now?
That's better. Thank you.
Okay, thank you. Then after defining the structural health monitoring, we will talk about something we are big advocates of, which is called active risk management. We believe that structural health monitoring and active risk management always should go hand in hand to really understand what our risks are and how they can be managed. Then for every typical project, we will talk, there's a systematic approach that we can implement. We are going to talk about the specific steps of that approach. In that, we will talk about system integration, how typical measurements, general widely applied measurements on different structures and how they can be incorporated into decision making. And then eventually that we are going to tie it up to how we can manage big data. It's become a bigger and bigger, one of the bigger problems actually, because we have so much sensor, we have so much other technologies that we can collect data, but the problem is how we should manage it and how we can make interpretations out of that. Then we will, towards the end, we will talk about some sample projects, real life projects we implemented, what the concerns were and how we created value. And then we will close it up with a summary slide. So what's structural health monitoring? Structural health monitoring, I always say this, is like a doctor-patient analogy. You can't visit your doctor just like a regular annual physical, or you might have problems that you want to see the doctor and diagnose what those problems are, and then basically work on those problems to fix. So the same analogy is valid for structural health monitoring as well. We have several different sensor technologies that we monitor structures with. We install these sensors to structures and collect data out of those. And then eventually that stored data can be post-processed or just visualized in real time. And then we can make interpretations out of that data. So that interpretation will eventually result in documenting the actual performance structures of the structure, as well as track actual performance. So why structural health monitoring is important and how it can answer several questions. First of all, we are just listing some of those in here, but of course there are so many various other areas that we can work with when it comes to health monitoring. First of all, we can validate the performance of our structure. Whether it's an existing structure, it could be a simple highway bridge, or it can be a signature bridge, or it can be a dam, it can be a building. You may have assumptions that you did during your design process, and then you would like to know if your assumptions are actually working out in the real world. So this is a good way of implementing a structural health monitoring project. Another thing is evaluate and control construction. A good example of that could be maybe a tunneling project or a big building or structure project where you need to look at the displacements along the construction, along the whole course of the construction, or vibrations that's happening around that construction area, or there might be some specific concerns with the ambient condition of that structure. For example, if you are building two bridges side to side, you may want to look at how the new one, building the construction of the new one, is affecting the existing one. So these structural health monitoring can help answering those questions. Another one is warn of safety and failure. If you are in charge of several dams in a huge network or several bridges in a huge network, or if you are monitoring, let's say, a nuclear power plant, you might have some tight margins that you need to look at every day for safety or potential failures. So structural health monitoring can give you a peace of mind for tracking, in terms of tracking those activities. You have existing bridges, you have existing structures. You know that that structure has been there for a while, and maybe that bridge or the structure is exposed to new load conditions. So you want to know if the new loading conditions, or just by the age of the structure, if there is anything deteriorating, or if there's anything you need to be concerned about. So in order to identify and reveal those unknown, structural health monitoring can help as well. Now you know the problem. You have your structure that you need to, and you know specific points where you need to do retrofitting, where you need to do replacements. Now you take the took action, you fixed everything, you repaired your structure, but now you want to know if your retrofit actually works. Now it's another area that structural health monitoring can help you. Eventually, when these things collectively come together, and especially for stakeholders that are managing a big network of structures, this is a great tool to understand what your risks are and you already know, considering that you already know how much fund you can allocate for repairing these problems. It's a good way of managing your assets and mitigating your risks. Several weeks ago, ASCE released the new report card for infrastructure. If I remember correctly, the previous report card had a grade of D+. Now it's C-, which means we are doing some of the things correct. We are in the right direction. However, going forward, we have a lot of aging infrastructure we need to work on and then basically fix and repair. And we all know that we have only limited funds. And the question is how we are going to allocate those funds to make wise decisions. Here are some highlights from that report card. For bridges, the report card says there are currently approximately 231 bridges that need repair work. And when it comes to dams, average age is over 57 years. When it comes to levees, again, the average age is over 50 years. And think about that. These structures are safeguarding millions and millions of people. And then maybe that's not going to be a good example, but several years ago, we have seen some of those bridges, some of those dams and levees fail and then risk the entire population living around that area. So structural health monitoring also can help to keep track of these potential failures and then over the entire life cycle of the structure. Another interesting highlight is about our roadways. 43% of our public roadways are in either poor or mediocre condition. So doing some pavement instrumentation, implementing some pavement instrumentation, and then looking at how new mixes are acting against the heavy loads can actually help us to come up with new design technologies, a new mix design, and then a better, more durable pavement system. Again, active risk management, as we said at the beginning of the presentation, and structural health monitoring go hand in hand. We define active risk management as a 5-step approach. So we start this approach by identifying our risks. So the question here is, what are the potential sources of risks? Here you see several pictures from several infrastructure projects. If you are a stakeholder looking at managing several wind farms, then maybe your risk could be your cracks in wind blades or some excessive vibration happening, some operational problems caused by the vibration. Or if you have a floating bridge, you might have problems with on your bridge caused by fluid structure interaction. If you are operating a stadium, your roof might be susceptible to some excessive snow and wind loads. Or if you are looking at a dam project, if you are managing a dam project, then your leakages might be a problem. Crack in the main body, solid body of the dam could be problems, or several others. Also, again, as we talked, pavement projects are posing risks because of heavy loads that they are under. So these are the steps that these are the examples how we identify our risks. So identification requires collaborative process of all stakeholders, including subject matter experts. Then the second stage will be the process where we quantify the likelihood of the consequences. Basically, this is the part that we do numerical quantification and integration of all risks. Then the next step will be planning stage. Make a plan for how risks will be managed. So this is the stage we will lay out a strategic plan for threats and opportunities, because every risk can also constitute a certain opportunity in there. Then we will implement structural health monitoring. Structural health monitoring, since at the planning stage, we know the key indicators that is going to tell us the risks. We are going to monitor those key indicators and then see how they change over time. In the control section, we will take action and then mitigate the risks based on the data we have collected. Then by completing the circle and do it actively, we will have a good asset management framework where we can do repairs and other remedies quickly, and then of course, without breaking the bank. Systematic approach is very important when it comes to implementation of structural health monitoring. 2-3 decades ago, it's a fact that some of the agencies, some problems have some unpleasant experiences with structural health monitoring projects. However, nowadays we have much better sensor technologies. We have much better system integrators in the market that know what they are doing, and then following approaches like this, and then making sure everything is working according to the plan, and then stakeholders are getting the best out of their projects. The first step, and maybe what drives the success of the project, is identifying the need. Again, going back to the past, some of the unsuccessful project is because the needs and objectives of the project are not identified very well. People are collecting data without knowing why they are collecting data and not looking at it. So that's a big problem. So for your projects, whatever structure you are working on, you need to identify your problem and basically what kind of measurements that you need to collect so that the problem can be easily solved. Then the next step will be designing your system. There are so many technologies, sensor technologies, data acquisition units out there. So you have to know what is going to work best for your project. By aligning your objectives with what kind of equipment you want to use, you are going to have a plan that's very well laid out and at the same time that is economical. Then once you decided what kind of equipment you are going to use, the next step will be planning and scheduling. The project site or the nature of the project might have some tight requirements, tight time limits. So it's very important to plan and schedule with the stakeholders so that nothing is going to be delayed. Then the next step will be procuring and testing your equipment. Although all the manufacturers provide their products with certain calibration and quality assurance documentation, it's always very important to test them in-house before putting in the field as well, just to make sure everything is right and according to what the paper is saying. Then in the field, you are going to install your sensors, and at every step of the way, you are going to record whatever you see in the field, any exception from or anything out of the ordinary you see, as well as typical readings of the sensors. Everything needs to be documented. So if you see a problem along the way, you are going to be able to pinpoint where that problem occurred and how you can manage that. And eventually, once everything is in place, you are going to collect your data. Based on how you are managing the data and how you are post-processing the data, you are going to interpret your results. And then according to what data and reports are telling you, you will take action and manage your structure. As we said, identifying our objective is in alignment with what kind of measurements you need to do. And measurements require different sensors and sensor technologies. Here, we are listing some of the most widely applied and well-known measurements and what kind of technology is out there. Of course, there are so many others. We are just listing some of the well-known ones. The first one is strain and stress measurements. This is probably the most well-known and very common. The technologies out there is generally resistant-based strain gauges, strain rosettes, or fiber optic or vibrating wire. Strain and stress measurements are quite popular in any aspect of bridge monitoring world, very widely applied. Acceleration is not as commonly applied as strain. Maybe on some of the specialized projects, we use acceleration measurements, and the technology out there is piezoelectric sensors, MEMS sensors, and fiber optic. Inclination and tilt measurements, generally, we are using these sensors for looking at soil structure interaction or some bridge move projects. And the typical technology is force balance sensor or MEMS sensors. If we are looking at construction management around a typical construction area, vibration, noise, and pressure measurements can become quite useful to basically avoid construction delays and deal with further litigation that could happen during or after construction or during construction. If we are looking at temperature correlations with other component level measurements, we use temperature sensors, and the technology out there is generally either RTD or simple thermocouples where you utilize the resistance difference between two wires. Displacement sensors, of course, there are so many applications, and they come as a resistance-based potentiometer technology, laser sensors, automated total stations, or nowadays, maybe HD camera. Computer vision applications are quite common nowadays, and displacement monitoring with cameras are becoming more and more popular. Crack propagation, basically you are looking at this, installing a crack gauge, which could be in terms of a strain-based gauge or a displacement-based, potentiometer-based gauge, and you are tracking the crack growth over time. Corrosion sensors are electrochemical-based sensors where we look at generally linear potential resistance. And the last two are settlement geometry, where we use GPS sensors, total stations, or vibrating wire settlement gauges. And finally, especially for signature bridges. A common application is to use wind visibility, temperature, and relative humidity sensors to eventually check the ambient weather conditions with various different component level measurements. We said that after identifying the object, it's time to design your system. By designing, we mean what kind of different measurement techniques you need to bring together, and then how and of course the way how they are going to interact with each other in terms of collecting data at a certain synchronization. Based on the importance levels to you, you are going to decide and then procure your equipment. After that, once you procure your equipment, you have to have a program where you test these all these modules in-house, which we call a factory acceptance test. So whatever you are going to put in the field, you have to simulate similar environments in your laboratory or in your workshop, and then make sure everything works according to the plan. Then, according to your plans, as you can see here, you will have for each location, of course, no doubt that the location of each individual data acquisition unit across your structure is also important, but we decided that on the design stage. Now, each location, we have to have a planned, very well laid out drawings showing that which component, how different components of the panel is interacting with each other, where the electricity is coming, how it's being distributed across the other units, and then how the data is being transmitted through the network. Having a plan like this is going to eventually help you in the future to troubleshoot certain problems. And after this, having this factory acceptance tested, having the plan in your hand, you are going to go out there, install your system, and as we said, at every step of the way, you are going to record everything through a site acceptance test procedure. For each and every unit that you install out there, you are going to do your field tests and then record everything on your site acceptance test sheets so that they can be reviewed later on, which eventually is going to help you track what happened in the field, and if there's any problem, review those problems. Now we talked about the design, procurement of several different sensors, how data acquisition can be tested and implemented. Now we will talk about very famous, very well accepted measurement methods and how they can be incorporated in the decision making. It's some examples. As we talked at several slides ago, strain and stress measurements are quite common, and the most well-known application is load rating. Currently, there are two different load rating defined, and I highly recommend everybody to check TRB e-circular about this, where they are talking about the state of the art of load rating, basically, diagnostic load testing, proof load testing, and how load rating can be, the real load rating can be achieved through these tests. Here you see a picture that one of our projects in Michigan, where there was a CFRP carbon fiber reinforced polymer based tandem based bridge construction, and then before it put into operation, we did load tests, and then here's another example in one of our projects in Connecticut, where we did load rating on a steel girder concrete deck composite bridge. Another application of strain and stress is stress concentration. If you have complicated geometries, if you have weird openings in your large girders, in your concrete members, you should expect stress concentrations around those holes or openings. So, or if you have welded joints, if you have bolted joints, larger joints, you would love to have an idea about how stresses are concentrated around those joints, and if they are in alignment with the design phase or not. Especially for steel structures, as you see here, steel girders, remaining fatigue life estimating the remaining fatigue life is an interesting application, which actually we have a slide we will talk later on, an application. And then eventually, this data collectively can be used for validating and calibrating your model. For each of these models, especially when it comes to load rating, 3D computer models, you have some assumptions that you are making, but let's say that's a 10-year, 20-year, 30-year-old highway bridge. You will have to have the right model, the cracks on your concrete girder, the boundary conditions, all those affect how accurate is going your model is going to be. So these measurements can help you to calibrate that model. Going over these pictures here, you can see one of our applications for a modular expansion joint, where we are installing strain gauges in a modular expansion joint, which can be used in fatigue life estimation, as well as stresses of these modular expansions over its lifetime. Here you are seeing a fiber optic strain gauge application on a panel point of a truss bridge. Another indirect way of using strain gauges can be thought in terms of load cells for pre-tension, post-tension members. Here is an example where we are showing some in-house built load cells. These are basically strain gauge embedded load cells that are calibrated in a laboratory condition and installed in the field. Here you are seeing a post-tensioning exercise in order to check how the validity of your post-tensioning levels during the post-tensioning process. We can use donut type load cells, strain gauge load cells, and look at how the stresses are changing. An interesting example, now that accelerated bridge construction and bridge moves are becoming more and more popular these days, another way of using these sensors could be during the bridge moves to look at the effect of potential wrapping or racking of the deck and how much stress is creating over different girders. Acceleration is not, as we said, not as widely applied as strain gauge measurements. However, there is maybe in automotive industry is very well applied and very well known, or airplane industry. However, there are certain ways of using acceleration measurements in structural world as well. By just looking at the time domain signal, of course, you cannot tell much when it comes to acceleration measurements, but there's a lot that we can learn from, as Larry explained in his presentation. There are, in the frequency response, we can see a lot of useful information. One of them is looking at the frequency shifts. Imagine that you have an accelerometer installed on a cable or in a girder of a bridge or any other component. They will have certain amount of stiffness into them. Of course, over time, we are going to see cracks developing or some degradation developing on these members. And then it's going to change the flexibility, stiffness of the structure. And eventually you are going to pick it up by looking at how the natural frequencies are shifting. Or now we just talk, what I just mentioned is just looking at these measurements at the component level. Now, if we have an entire spatial distribution of several sensors across the structure, then it is possible to get the overall model response of your structure. What could it tell us? I mean, when you are at the design stage, of course, you are looking at your computer model is going to give you certain mode shapes based on how you define your design spectrum. But actually, how it is behaving in the field is a mystery. So accelerometer measurements can reveal that, so that you can eventually, by looking at the difference between field measurements, field model shapes, and computer model shapes, you can mitigate the differences and have a correct model. One of the other applications is cable force prediction. This is basically Newton's law of F equal m times a. It's not a super sophisticated way of putting that, but basically when you have the acceleration, you can, through Newton's law, you can calculate the cable force. If you are collecting your data at really high speeds, we are talking about 100, 200 kilohertz, it is possible, and we are going into acoustic range, of course. Yeah, we can say something about potential wire breaks in your especially cables or post-tension members. We already talked about the finite elements calibration, and eventually, like strain measurements, if you have, let's say, some if you are looking at a pedestrian bridge where you have vibration problems, and then you decided to install some mass tuned dampers or some extra dampers that you are going to, you are expecting to mitigate the problem. Now, by looking at the acceleration measurements after retrofitting, we can say if that retrofitting actually worked or not. Inclination and tilt can be told about like static or dynamic, two folds, static measurements or dynamic measurements. Generally, we use this type of measurements at the pier in bridge, specific bridge case on the connection of piers with the girders. When they are installed on the piers, we can say something about the soil structure interaction, if the pier is moving, rotating, if there's any problem with the soil foundation, or looking at how the connection and bridge connection between the bridge pier and the girder is changing over time. We can say something about the certain skewness of the girder. In some of the signature projects we have done in the past, we installed these in, we installed some dynamic dynamic inclinometers where we are extracting the dynamic rotational modes of the structure, as well as especially for high-rise towers, high-rise building, we are looking at how the strong winds affecting the rotational response of the structure. Another interesting application, as you see here, is bridge bearings. Looking at the rotation of bridge bearings can tell a lot about how the loads from the girders are being transmitted to the piers. The vertical alignment of the force from the girders to the bearings are quite important, and this is a way of tracking that. Also, several other applications can be thought in terms of bridge moves. Here you are seeing an interesting example, HUP long bridge truss erection. During this project, we were able to install several displacement gauges as well as inclinometers over the entire course of the erection process, so that in real time, stakeholders were able to see how the rotations were changing and if there was any risk. Displacement measurements are quite common. What we are trying to answer here is how the temperature effects, how the traffic effects are, or if they are affecting the age of the expansion joints or other structural members. Here you are seeing an interesting example of a string potentiometer installed at an expansion joint. So the information we can extract from this is the daily, seasonal, and then annual cycles of displacements. If the modular expansion is behaving as it's supposed to, if there is any part that's frozen, that's not moving at all, you will be able to tell something about it. And eventually, by looking at through a regression model and looking at how the accumulated displacements are changing over time, you will be able to say something about the remaining life of the expansion joint. Here you are seeing an interesting example of a laser sensor, basically looking at the pier movements between relative to two pier movements. And then here you are seeing an example of what we talked initially, looking at by installing the laser displacement sensor along this truss, we were able to capture out of plane behavior of the truss members. Another common example is corrosion measurements, corrosion sensors. These sensors can be installed either at a later phase on an existing structure, but it's always better to install in an embedded fashion at the beginning of a new construction. If you have, it's possible that we can install these sensors in a network fashion. If you have, let's say, 2 or 3 kilometer long bridge, these sensors can be installed in several different members. So eventually it's going to create a corrosion map of your structure, so that over time you will know where potential corrosion risk has started, and if it's at the level that you need to take action and remedy, or you can defer it to a later stage, or how they are interacting with each other. Or for existing structures, that you know there is corrosion, but you want to know how fast it's progressing and if it's at a level that you should be concerned about. By implementing some corrosion sensors in that specific structure, you will be able to say something about the corrosion rates. Settlement and geometry is something that we generally use for tracking the overall geometry of the structure under traffic, under daily, seasonal, and accumulated ambient conditions. When they are installed in the abutments, we can look at the abutment settlements. And if we are also sampling it at a high sampling rate, we can even extract some dynamic information out of the structure as well. But generally, the most useful application, the best value we can get out of when it comes to these sensors is basically settlements most of the time. Here you are seeing an interesting example from Chesapeake Bay Bridge and Tunnel project. You are seeing the entire island being monitored for settlements in real time. This is our last example. One application that's becoming commonly applied is weather station measurements. The importance of this application is twofold. One is for post-processing analyses of weather measurements, wind speed. This could be wind speed, temperature, with the component level measurements. And I mean by looking at their correlation and looking at how they are changing over time. These measurements are quite useful. But at the same time, for areas where the commercial traffic is quite important, when there are extreme weather events, making these decisions are quite important. Stopping the traffic for a commercial reason can cost, of course, a lot of money. And this is a great way of understanding where you are standing in terms of wind speeds and in terms of if there's anything in that daily operation that you should be concerned about or not. Now we talked about measurements, and then the next step is going to be how we are going to manage that. It is possible with this new high-end technology to collect this data at really high speeds and at the desired level. Of course, we have the technology, we have everything that in our reach to get this data. But the most important question, one of the most important questions is how we are going to manage it and what that data is going to tell me. That's very important. Here we are talking about a system where we see that has potential. It's being applied currently and then has a huge potential for stakeholders. Basically, we are talking about a data management, web-based data management system, web-based or standalone, I should say, data management system, where you have any kind of sensor technology you can think of, any kind of data acquisition technology you can think of, accumulating in a central system. Nowadays, of course, web-based, cloud-based data storages and data management systems are becoming quite popular. But we are talking about a instrumentation and monitoring, structural health monitoring specified system. This system can store your data, but at the same time, turn it in a consumable form, so to speak. Let's say that you are getting some strain measurements, right? Pure strain measurements. Imagine that most of the cloud-based system is going to give you a time series data structure. You are looking at basically your X direction is going to be your time, and Y direction is going to be your magnitude for most of your sensors, time domain signals. However, it's quite valuable to see all these measurements in a spatially meaningful form. Here you are seeing a GIS map where you know where all your sensors are located, and then by looking at the geometry of your structure and how these readings are changing over time, you are sort of, in a way, looking at the patterns between those measurements. This is quite useful because sometimes just by looking at one time series data cannot really reveal everything. You have to see your structure as a whole body. For example, here you are seeing if this was a bridge project, let's say, looking at a settlement of one point may not tell you everything. you have to look at how the surrounding components are behaving and how their behavior is changing over time. So this is a great way of tracking that. Here you are seeing an example of a TBM going under a very densely populated area. And then as it moves forward, you are seeing your displacement changing in real time, as well as your potential vibrations. So this type of application gives the user the total control of the project. If you have concerns that you need to, thresholds that you shouldn't exceed during the lifetime of that construction, you can implement those in your measurements, and the system will alert you when they are exceeded. And every morning when you wake up, if you are managing a very important project, you will have a peace of mind that everything is going according to the plan. And it's just going to be at the tip of your fingers. Your tablet, your phone, you're going to be able to reach this entire data set. You are going to be able to create your reports and look and do your own interpretations by looking at that. An interesting example of such an application is New Tappan Zee Bridge. We are quite proud of this application. Here, I am going to give you some highlights of the project and how we are aggregating a massive amount of data every day down to a consumable form. We also approximately have 133 high-speed data loggers collecting approximately, for every sensor, collecting approximately data at 60 hertz. Some of these loggers are basically made by us. Some of them are from different manufacturers. And the beauty here is that they collect this data in a certain synchronization and then transmit data this data through a network to a central location located right near the bridge. This data is collected from more than 800 sensors. And then the raw amount of records that we collect each day is 3.9 million. Now, of course, when you look at this massive number, it's scary. However, we are turning into an aggregated consumable form for the user. In that, basically, we are calculating for every high-speed interval, 10-minute interval we are collecting data, we are turning into statistical form. So you are looking at for every 10-minute high-speed full resolution data, you are looking at minimum, maximum, average value, standard deviation, and certain other statistics of your data. Those are the ones those are the type of data that we are storing. But at the same time, we are not sacrificing the value of the full resolution data collection. At random times during the day, at certain events like, let's say, extreme weather, earthquake, ship impact, we will never sacrifice the data. We will never lose data because the system is smart enough to understand what's going on and then collect that data. And eventually, all that aggregated data, statistical data, is being turned into more than 30 different types of statistical and post-processing reports. Through these reports, the user is able to look at the interaction of different components, as well as the overall behavior of the bridge. Several smarts that we have implemented in this project is collecting data based on triggered events. So as I said, the system is smart enough to understand if there is an extreme event happening around the structure. So let's say this is in the form of setting some thresholds to certain sensors, as well as this could be some time interval, triggered time intervals set by the user. So we are only collecting full resolution data to be post-processed by the user later on to understand the before and after of the events through these triggered events. Also, another important thing is to present this data to the stakeholder. Collected data, and if you are looking at collected data at full in terms of statistics, can also become quite huge when you are looking at 10 years, 20 years of data. And considering that this bridge was designed for more than 100 years design life, at maybe 10 years, 20, 30 years from now, of course, the user would like to know what changed, what was it, what was the condition at the beginning, and how it changed over time. Bringing this type of data, it's an observable form is quite challenging because you are limited by the hardware of your system, hardware of the computer you are using. So we have implemented some smarts to bring this data at a very fast pace without sacrificing the important signatures of the structure, which we call data tiering. And eventually, all these reports that we are creating in the system are based on certain things that are defined in the specification. So, for example, weigh in motion data is being collected through some source, through desired statistics, or strain information can be turned into stress information, or expansion joint displacement sensors can report the accumulated displacements from the time that they are installed until now, so on and so forth. After talking about big data management, now we would like to go over some sample projects, which we think that can give you an idea about how SHM can help for your own needs. This is an interesting story where we worked with CME Associates and Mass DOT. This project was done on I-91 Springfield Viaduct. The problem was with the hanger plates not behaving, of course, as they were designed. And the other problem was several cracks in different girders on the webs and across the structure. When the condition rating is taken into consideration, we will have to replace the entire bridge, which would cost $800 million. So, of course, the concern was is this the actual performance? Is this the actual condition of the bridge, or we are just condition rating is kind of misleading at this point? So what we did was, working with the engineers, we looked at the remaining fatigue life by collecting the stress cycles under traffic loads. We estimated the remaining service lives, fatigue life of steel members, as well as we looked at how the superstructure loads were being transmitted to foundations through piers. Eventually, the decision was made that with several remedies, by changing some of the, by repairing some of the steel girder components, and then repairing the deck, Massachusetts DOT was able to save $550 million. And the money invested in this project was approximately $180,000. So it's a great value, it's a great story. And we would, especially when, if we again think about what we talked at the beginning of the presentation in terms of bridges, 1,000 bridges that we need to remedy, these kind of studies are quite essential. Because if you also look at the past, most of the, especially load rating experiments, not experiments, but nowadays it's DOT experience I'm talking about, reveal that our designs are quite conservative, and most of the time the agencies do not really go through total replacement of the bridges. Just by making some repairs here and there, it's possible to extend the service life of these bridges. Here's another example where we worked with Skanska and Kiewit, as well as Port Authority of New York and New Jersey. It's Bayonne Bridge. As you remember, there was a huge renovation on this bridge until recently. And we were the company who helped the engineers to understand, to basically address their concerns. The concern was basically they raised the deck, and then the geometry was the concern. If they wanted to control the geometry and during the erection process. And the other concern was, after doing the renovation, how the loads would be transmitted through the piers to the foundation. And then the last one was the surrounding area, the buildings, the public, how the vibrations are affecting everything, if it's causing any cracks or unexpected displacements around around the construction area, which eventually can create huge litigation problems. So by doing some instrumentation as well as looking at vibration levels around the construction, we were able to provide a controlled bridge geometry control, and then we verified that everything in terms of load transfer was according to the plan. Another interesting project, this is not typically a bridge project, but another important project is East Side Access, where we work with MTA. It was a quite challenging project in terms of timing intervals that we had. Whenever we had to go there, of course, we only had tight working intervals. But the things we did here was checking the displacements as the construction was ongoing, making sure that displacements was within the threshold defined earlier, as well as the vibrations around the vicinity of the construction area, to make sure that there was no damage to the surrounding structures. By doing that, of course, we prevented the potential construction delays, as well as provided early notification to both the contractors as well as the public around that area for certain problems. Another example, again, thinking of that dams and levees are over 50 years old and they concern a lot of risk. Looking at the overall shape deformation of dams and levees, as well as how they are interacting with soil, as in this example, we can say something about if there is anything of concern or not. Here you are seeing extensometer installed along the wall, as well as GPS system to track the settlements. We are able to tell how if it's anything that the stakeholders should be concerned or not in terms of safety. And I think this is our last example. Payment instrumentation is probably not very well known except the people who are in this field. Generally, the concern here is the performance of the new mix, asphalt or concrete, it doesn't matter. Here you are seeing an example of a Honolulu Airport taxiway instrumentation. We installed longitudinal and transverse strain gauges to understand the behavior of the new pavement design under heavy plane loads. If the design and performance was successful here, it would have been implemented to the entire taxiway. Another example that we work with Dallas Fort Worth Airport here for the concrete pavements. We installed concrete strain gauges, pressure cells, or compression gauge to understand the performance of sub-base as well as subgrade, and then to confirm eventually that their design was acceptable, or if they can apply it around the entire region, around the entire airport. Summary, just 3 points, I think very important points, is that structural health monitoring is a great way of tracking your risks and mitigating those through objective data. And then eventually with an active risk management, it's going to help you to protect your assets and then make wise decisions as to how to allocate funds and how to attack your problems. And then eventually, if there is any problem with your structure, solve them effectively and on time, so that it's not going to propagate and make bigger problems. Thank you so much for your time.
Thank you so much, Ozan. Sorry, Alan, were you saying something?
No, go ahead.
So, well, and I've seen that presentation a couple times now, and it's just so interesting and full of really good information for our attendees today. So we have a few questions here and time for a couple of those. So we'll start with this one. The data management and reporting is very interesting. Are clients also looking to connect this data to event triggers to their traffic management systems and incident management centers beyond just the weather and camera feeds for real-time management?
I think they are talking about connecting this directly to rain motion systems I believe.
No, I think they're saying, Ozan, that we take the sensor readings and feed those back into active management of the structure. So for example, if we have a sensor that says we're exceeding on a strain, do you then stop traffic on the bridge?
Oh, okay. Well, it is possible, of course, because every sensor has a threshold set on them, defined by the designer. So if there is any exceedance of those thresholds, the first line of action is basically looking at the data, looking at the reports, and if there's anything of concern, and that decision can be made quite easily by looking at that. Yeah, it is
I'll
possible.
add to that, Ozan, a bit in that we're not doing it without human intervention right now, though.
Yeah.
Our systems really aren't smart enough to capture spikes in data and discard those. So we use the systems to raise alerts to people in real time, and then a person makes a decision: is this a valid reading? Is this a cautionary situation? But one of the advantages of these systems is as Ozan pointed out, is we are able to identify fairly quickly if we have a sudden load like an earthquake or a big wind or an impact, and recognize that so that people can make decisions in a matter of minutes, not hours.
For sure. And I'll just add to that, that this is certainly a direction in which people are looking to go. We're not there yet, but even if you think about wind turbines and people who are looking at vibration monitoring and then feeding that information directly back as a loop to say, okay, now we need to slow down the rotation because we're exceeding the strain levels. So, or we're exceeding the vibration thresholds. So it's certainly a direction that people are headed, but we're not quite there yet. We still need some engineering decisions to be made. Another question is, how do you use SHM on old bridge foundations?
I think at this point we are looking at. It's just going to be probably looking at, and Ellen, you can probably build on that because you are more geotechnical. For as a person who is looking at only superstructure, I believe it's going to be limited by looking at the rotations on the of the pier to understand, and settlements of the pier to understand if there's an ongoing movement or if there's an ongoing suspicious behavior. Then I believe the next step is going to be understanding what's actually happening beneath the soil, which is going to require another approach.
Let me jump in here a little bit. This is a huge challenge right now. And in fact, it's the subject of a study that we have going on at the moment with the Federal Highway folks or the NCHRP folks. How do you quantify the behavior of an existing foundation and its ability to work in the future? How long life might it have? Can I add more load to it? It's a huge challenge. And just even knowing what that foundation consists of right now is very difficult to do in an efficient way. Mr. Olson has some techniques where he can use some of the pulse echo, for example, and try to get pile links in certain circumstances. This is a big research challenge we face, and there are no quick, easy answers. The most reliable is if you can do a visual inspection, so you can try to see what is the condition of the materials, corrosion-wise, cracking-wise, followed by maybe trying to do some kind of loading. So people have done some work where you're looking at the response of the foundation to some type of dynamic load, and from our load test, and then from that try to infer how it might behave in the future. But that's a big extrapolation too, and a challenge for us.
So I think you touched upon this in your presentation, but this is a good question, and maybe we can talk about it a little bit, and it might be the last question, but is the structural health monitoring program designed for the design life of the structure? And if yes, how do you check instrument drift? Can you recalibrate?
Of course, it's always possible. The drifts are when everything is installed based on standard operating procedures. We are actually not expecting sensors to reveal problems like drifts or any other suspicious data spikes and all that. With proper grounding, proper application installation, we are not expecting those problems in short term. However, of course, these are electronics, some of them complicated, some of them are just less complicated, and those problems can happen. There are several ways we can understand if a certain reading is acceptable or not. One of them is basically you can set thresholds on set sensors. And then whenever, let's say there are spikes, there are huge drifts that you are not expecting, eventually that sensor reading is going to go over those thresholds. So when it happens, the system will alert you to look at that. And at that point, you will have to look at the data and decide if there is something that you need to be concerned about or not. Well, a good way of looking at it, if the reading is legitimate or not, might be checking some redundant sensors or other sensor behavior around that region. So that's a way of looking at it. Other than that, if the data stops, we have smarts actually that we know that the data stopped and they're not coming in.
Thank you. And I think that's all we have time for today. But again, we will get all of these questions out to the attendees with answers. So if you had a question here that we didn't get to, I apologize, but we'll get those out to you through email.